All right, let's get right into it. You know, our bodies are these absolutely incredible machines. But just like any machine, parts can wear out. And when you're talking about our most essential plumbing, our blood vessels, finding a good replacement is, well, it's one of the biggest challenges in all of medicine. We're talking about the quest to create a living, breathing spare part, basically from scratch.
And I'm not exaggerating. For decades, scientists and surgeons have been on this epic search for what they call the Holy Grail, a perfect, off-the-shelf artery that's ready to go whenever a patient needs it. It's a quest that could save millions of limbs and lives. And today, we're going to see just how incredibly close they are to actually finding it.
So why is this such a big deal? Why do we need to replace blood vessels in the first place? Well, we're talking about some really critical procedures here. Things like fixing a life-threatening aortic aneurysm, a bulge in your body's main artery, or bypassing clogged arteries in the legs to prevent an amputation. And it's also a lifeline for patients who need hemodialysis. The need is massive, but the tools we've had, they're just not perfect.
Right now, surgeons have to make a tough choice. On the one hand, they can take one of your own veins, usually from your leg. And that's great, because it's living tissue. But you only have so many to spare. It means another whole surgical site, and sometimes those veins just can't handle the high pressure of being an artery. Then, on the other hand, you've got synthetic tubes. Think materials like Gore-Tex. They're always available, which is a huge plus, but the body knows they're foreign objects. They can get infected, they can cause blood clots, and they never, ever become a real part of you.
So the dream vessel, the perfect solution, has to have the best of both worlds, right? It's got to be super strong to handle all that blood pressure. It needs to be sitting on a shelf, ready for surgeons whenever they need it. It has to be safe, resisting clots and infections. And here's the magic part. It has to somehow become a living, functional piece of the patient's own body. That is a very, very tall order.
To really appreciate how far we've come, you have to look back. I mean, this quest for a better blood vessel is not new. It's a story that's built on more than 100 years of incredible innovation and, let's be honest, a lot of trial and error.
You can just see the progress step by step. It starts way back in 1912 with something we take for granted now, just figuring out how to sew two blood vessels together. That was a Nobel Prize-winning discovery. Fast forward to the 70s, and we have the synthetic plastic tubes that are still common today. Each one of these was a huge leap. But you see what's missing? None of them solve that core problem of creating a living replacement.
So the next logical step was to try using actual biological vessels from other sources, right? Like specially treated arteries from animals or preserved veins from human cadavers. The idea was sound, but the body is smart. The chemicals they used to prevent your immune system from rejecting these tissues also made them totally inert. They were just dead tubes. They couldn't be repopulated by the patient's own cells, which means they couldn't heal, they couldn't remodel, and over time, they'd just degrade, weaken, and eventually fail.
And this is where the story takes a really fascinating turn. Instead of trying to tweak an existing vessel, scientists started asking a totally new question. What if we could grow a brand new one from the ground up? And with that, the field of tissue engineering was born.
Tissue engineering is really the secret sauce that makes all of this possible. It's basically the science of creating living, functional tissues. And you do it by combining three key ingredients. You need a scaffold for structure, you need living cells as your building blocks, and you need the right cues to tell those cells what to do and how to grow.
Okay, so how do you actually build a blood vessel in a lab? This process is just incredible. First, you start with a tube-shaped mesh made of the same kind of material as dissolvable stitches. Then you seed this scaffold with smooth muscle cells from a human donor. Next, and this part is brilliant, you put the whole thing in a machine called a bioreactor, which pulses nutrients through it just like a heartbeat. It's literally exercising the growing tissue, making it strong. Over about 2 months, that original mesh completely dissolves, and what you're left with is a tube of pure human tissue. But the final step is the real magic. You gently wash away all of the original donor cells, leaving behind this perfectly formed, clean protein scaffold, a ghost vessel that won't trigger an immune response in any patient.
And that incredible process leads us to a technology that is now in the final stages of clinical trials. One of the most promising examples is called the Human Acellular Vessel, or HAV for short. So let's take a look at how this thing actually performs in the real world.
First off, let's talk about strength. This table shows burst pressure, basically how much pressure a vessel can handle before it fails. Now look at a healthy human vein, the kind they often use for bypass surgery. It bursts at around 1,600 millimeters of mercury. This bioengineered vessel, it holds on until over 3,300. That is more than twice as strong as your own vein. It's even stronger than the internal mammary artery, which is considered the absolute gold standard for heart bypass grafts. It's unbelievably tough.
But honestly, being super strong, that's only half the story. The truly revolutionary, mind-blowing part is what happens after it's implanted in a patient. This isn't just a static pipe, it's a template for regeneration.
And this transformation is everything. As soon as the vessel is in the body, the patient's own cells see that protein scaffold and they think, hey, this looks like home. They start to move in. Smooth muscle cells migrate into the walls, rebuilding them and giving them elasticity. And crucially, endothelial cells, the body's natural Teflon coating, they grow a brand new non-stick lining on the inside. So that acellular graft gets completely repopulated and becomes a brand new, living, self-healing artery that is 100% the patient's own.
So the big question, does it work? Well, in phase 2 trials for dialysis patients, which is a really tough group, the results were fantastic. This number, 89%, is the secondary patency rate at 1 year. All that means is that after 12 months, 89% of these grafts were still open and working perfectly, maybe with a few minor tune-ups along the way. In this field, that is a huge success. And there's another massive benefit. Get this. Across multiple studies with over 150 patient years of data, there has only been a single reported case of the graft material itself getting infected. Now, if you compare that to synthetic grafts, where infection is this constant, serious risk, well, this resistance to infection is an absolute game changer.
So it's pretty clear this technology is right on the edge of totally changing vascular surgery. But the innovation is not stopping here. Let's take a quick look at how this is all building toward an even more incredible future.
Now first, it's really important to say that the big, large-scale clinical trials are still happening right now to confirm the long-term performance of these vessels. But for the first time in this century-long quest, that holy grail, a truly off-the-shelf regenerative blood vessel, it really feels like it's finally within our grasp. And if we look even further ahead, the technology just gets more precise, more futuristic. Researchers are now developing 3D bioprinters that can literally build a custom blood vessel layer by layer using something called a bioink. Think of it as a 3D printer cartridge, but it's full of living cells and gels. And others are using a wild technique called electrospinning, which uses powerful electric fields to create these ultra-fine scaffolds that perfectly mimic the complex natural structure of a real artery.
And all of this leads to one final, huge thought. If we can successfully grow a relatively simple tube like a blood vessel, what's next? The same exact principles, combining scaffolds and cells and cues, are already being used to try and build much more complex tissues. So the question isn't just about spare parts anymore. The real question is, are we standing on the edge of an era where we can 3D print custom organs on demand? It turns out the quest for the holy grail of vascular surgery might just be the first step in a complete revolution in medicine.